This conference will now be recorded.
Okay. Fine. Fine. So, in the last class, we started talking about, or we initiated our discussion talking about models, right? So basically, we first we tried defining what exactly a model is. So a model is nothing but it's a replica, right? Now, a model is something, it's a replica or it's a replication of some business environment for us. So basically, if I'm trying to predict my EAD, I'm trying to develop a model. So I'm trying to build out those representative characteristics which becomes essential in determining the exposure at default for a bank. If I'm trying to predict the loss given default, I'm trying to identify those factors which are representative in defining the loss given default. So over here in this particular part, we talk about as we talk about model development or modeling approaches. So we started talking about the key risk drivers. So we started talking about those key factors which explains the riskiness associated with a loss given default model, with an exposure at default model, and so on. Right? Now, the question that comes out to us is then what exactly is a model? So, a model is nothing but it's a relationship between an independent variable and a set of independent variables and a dependent variable, which we call causality, right? So, our objective is to assess the causality that exists between a dependent variable and an independent variable. Now, talking about causality, what we got to see is, or we talked about, is that talking about dependent variables, broadly, there are two types of dependent variables. One is a categorical dependent variable, the second is a continuous dependent variable. So, these are the two set of dependent variables that we get to see, right? Now, the next part was so the continuous dependent variable. Now, talking about the continuous dependent variable, so basically, if we have a continuous dependent variable, the modeling approach that we take up is linear regression. If we have a categorical dependent variable, the modeling approach that we generally take up is a logistic regression, right? Now, the question that comes out to us over here is that how do we then start assessment of this? So, our basic objective is to start with understanding of the linear regression model, right? So, the linear regression model. So, when I talk about the linear regression model, what I'm talking about is a continuous dependent variable and an independent an independent variable which can be linear or I mean which can be continuous or categorical as well. Now, the one thing that we got to clearly see in the last discussion was that that when we talk about regression, what we are trying to talk about is mediocrity. What we are trying to do in a regression is that based on a historical average behavior, which is observed in the past, we are trying to predict the average behavior that can possibly occur in the future or in a forward-looking time span. But but there is always a difference between the predicted values and the observed values, and that is because of the existence of the random term, of the error term. Now, this error term is something which we cannot model. So this is an unknown, or this is the component which talks about the unknown occurrences, about random occurrences, randomness in the future, right? Very simply think about a fact that you give uh, one exam 3 times, right? Let's say you're appearing for your GRE exam and you give your GRE thrice. You put in the same level of effort, the same question of the same toughness comes in. You work with the same sincerity, everything else remaining unchanged. It is highly possible that you will never score the same score in the 3 GRE exams because there are certain random element of randomness, right? Or there are certain random factors which are always operating, right? So the issue that happens over here, the randomness that comes out over here, that comes out from here, is because of some third unknown factors. And had this unknown factor been not there, then predictive modeling would have not been really something which of interest to us, right? So this is where this entire thing becomes very important. So the entire existence of a predictive modeling industry is based on the existence of this of this uncertainty in the future, which we need to minimize, right? So we talked about. So what we saw over there was that when we talk about a regression model, we are trying to find out the conditional expectation of the dependent variable given a value of the independent variable. So what we are trying to always predict is the expected value of y given x. So expected value of y given x equals to x is something which we are always trying to model in any regression framework, right? So we started off talking about the population regression function. We started talking about the sample regression function. And from this perspective and from this particular point, what we have done is we have kind of created the dependent variables. So we have kind of created the the dependent variable. We have kind of created. So we talked about the predicted value of the dependent variable. We talked about the alpha hat. So basically what we talked about was the population regression function and the sample regression function, right? So we know that the population is not really known to us. So what we generally do is we use the sample regression function to frame an idea, to frame an estimate of the linear of the population regression function, right? And now this particular model has been based on certain assumptions. So what are the important assumptions that a linear regression model follows? So I am repeating this because this assumption of a linear regression model is a very potential question in any credit risk modeling interviews, right? So the first point is the independent variables and the dependent variables must belong to the set of real numbers. So they must be real in nature. The numbers should not be complex numbers. The second is dependent variable has to be continuous in nature, while the independent variables can be a mix of continuous and categorical variables. The third point is the independent variable must be non-stochastic in nature. Number fourth is the model has to be linear in parameter, but not necessarily in variables, because the variables are non-linear. You can apply certain transformations and do that. But if your model parameters are non-linear, it means your system is a non-linear system and you cannot linearize parameters. Your model
Can you
has to be
please
linear in terms of
can you please
yeah,
can you please repeat the fourth point?
yeah, I'm coming to it. I'll just repeat it. So what I'm saying over here is that the model has to be linear in parameters, right? But not necessarily in variable. Now, what do I mean by linear in parameters? See, if your model is non-linear in terms of its variables, let's say you have a x which is non-linear. Or what do I mean by non-linear? What I mean by non-linear is that your variable is not showing a full linear trend. So very easily what you can do is you can do some kind of capping, flooring, transformations and things like that, and you can get it into a linear trend, right? So your variables can be non-linear because of the existence of outliers. So if you cap them, you floor them, or you look into the 99th percentile value, you cap it using that. You do some other exercises, and then you can reduce the variable. You can create the variable into a linear variable. You can make the variable behave linearly with your dependent variable. But if the model parameter is non-linear. Now, what do I mean by a non-linear parameter? Whenever we write any equations, right? So the linearity or the non-linearity of a model is determined by the linearity of its parameters. Because if its parameters are not linear, then the system that you will also have will be a non-linear system. Now, what are non-linear systems? Non-linear systems are higher order systems which which have very complex behavior. In a linear system, what happens is the proportional behavior, right? Now let's think about a behavior which is convex in nature. So in that convex in nature, what you can easily do is your parameters keep on multiplying or getting squared up, cubed up, something like that. Let's say you have an equation y equal to mx. So that is a linear equation, right? You have a equation y equal to m square x. Now, no matter what, you cannot change or you cannot linearize that m square. You can linearize x if x is non-linear because that's the variable. But if the parameters in the model are non-linear, then you cannot do that. If now, what do I mean by linear and non-linear parameter? If the parameters are linear, it means that the model, the dependent variables are responding proportionately to the dependent variable. If the model is non-linear, it means that it is not responding proportionately to the dependent variable, right? Now the next question is, now the next question that comes out over here is that how do I know whether a model is a non-linear model or not? So basically, models which fit a convex graph, concave curve, or models which are chaotic in or systems which are chaotic in nature are something or are examples of nonlinear systems. Now, high example of nonlinear systems in a day-to-day world is seen in um your this thing in stock markets. So stock market models are nonlinear models, right? So they are not typically linear models. But so any systems, let's say weather systems or systems where there are a lot of repercussions involved, right? Let's say uh, let's say there is a system which is built such that where small disturbances gradually build up exponentially into exponential disturbances. So like it's a very famous example of this is the butterfly effect, right? So what is the butterfly effect? The butterfly effect is, let's say, so the basic question that it actually try to posit is that if the, you know if a butterfly flaps its wings in some parts of Canada, is it possible that that turbulence creates a, a hurricane in California? So, so what I mean to say is where systems build up exponentially. Let's say, for example, why am I saying this is for stock market? Because let's say there is a small speculation about an asset in the stock market, right? And the news spreads in the market. The moment the news starts spreading in the market, the impact of that is felt in an exponential manner. 2 buys from 2, 4 buys from 4, 16 buys from 16, 32 buys, from 16, 256 people buys from 256 is squared up. So the response every time exchanges by 1 unit, the impact on Y happens more than proportionately what you generally see. So if for every 1 unit increase in X, the impact on Y is much more than uh, so every time it happens, the thing increases. So the growth rate of the growth of the growth rate increases over a period of time, right? So these are non-linear movements. Now, if such a thing happens, then a linear system will always under predict the values, right? So basically, for most of our cases, luckily in the banking system, you don't see such thing because there has to be an underlying mechanism which causes the impacts to explode, right? Now, so over here in most of our cases, we see that the models are linear in terms of their parameters. Right. Now, to ensure that there is linearity of parameters, non-stochasticity of X itself ensures that there is non-linearity, ensures the linearity of parameters. How it shows, what it does, I'll talk about that later. Right. But is this point now understood? Are you clear about this? So, in a layman's term, what we are trying to say over here is that the system builds up, right? So the model is non-linear, is linear in parameters. It means that the x, the y always responds in a proportionate manner to unit changes in x's. So y increases at a constant rate in with respond to in response to one unit changes in x, or to each unit. Each time x changes, y responds in a proportionate manner.
Tanmay, here when we say that the variable should be non-stochastic in nature, what
Mhm.
exactly does it imply?
Okay, so I was just about to come to that. In the last class, we had discussed this part. You remember this explanation, Akhilesh?
Yes, Tanmay,
Okay,
yes.
I'll just recoin the example once again. Now, over here, if you have a look into this, I'm saying that okay, the EAT is explained by the utilization. Let's say there is a credit card, right? The higher the utilization that a borrower has on a credit card, higher would be the exposure that the borrower is expected to have, right? So now if I try to predict that using the expect exposure at default, what you see is the utilization is 0.85, right?
Yes.
Maybe 2000, 2500. Now observe that there are two readings of 0.85. But every time the utilization was 0.85, the EAD value was very different from each other, right? So given a utilization, the EAD is not always the same. Now, so then what we need to then what is the outcome like? What I'm saying is that if you look into the utilization series, it's a distribution, right? So utilization will have a distribution attached to it. Now, yi will also have a so xi will have a distribution attached to it. The ui also has a distribution attached to it. What it means is that every time I'm trying to pick out a value from utilization, there is always a probability associated with it. So it means that the entire right hand side of the equation is stochastic in nature. So the prediction that I'll make for yi will also be stochastic. But I don't want that. So the prediction that I'm going to make about y should be non-stochastic. So what I need to do is I need to make xi non-stochastic. So I need to remove the distribution from xi, right? In order to do that, what I do is I remove the distribution from xi and I put it on yi. How do I do it? What I say is that fine, I'll not predict each individual value of y. I will predict the conditional expectation of y given a value of x. So what it means is that every time the utilization has been 0.85, I look into the EAD values, the distribution of the EAD values that occur corresponding to 0.85, and I'll try to compute an expected value for that. Or I'll try to find out the average value, the average exposure at default that can be there if the utilization is 0.85. So given that the utilization is 0.85, what is the average what is the average EAD that I can expect out of that group, right? Now the moment you do that, so the moment I draw this table over here, right? So given 0.85, this is a distribution of the EAD, right? So the moment I do that, I'm shifting the distribution to the dependent variable EAD, and this utilization becomes a becomes a non-stochastic variable. So what I mean is that okay, given that it is 0.85, now when I put it as given, I am taking out the distribution of the independent variable x, right? So what I say is that given that it is 0.85, utilization 0.85, what is the expected value that y has? So when I'm computing the expected value of y, I'm shifting the distribution to y. and I am making x non-stochastic. So what it means is, now when I'm trying to predict the value of yi given x, so x is non-stochastic, it means x is a simple number. It does not have any distribution attached to it. So it is a deterministic component in the entire regression model. So all the x's that we have with us has to be non-stochastic. So there should not be any probability. Otherwise, the entire prediction becomes random. So we needed to find out a way to decide, to identify whether this distribution was coming out like that. And what we got to see over here is simply that the utilization. So when I write it like this, when I take expected value of, when I'm trying to find out the expected exposure at default, given the x equal to 0.85, I know that okay, whatever I am doing is, so x becomes non-stochastic for me. Correct?
Yes. Yeah.
So when I say x is non-stochastic, or I'm trying to make x non-stochastic, what I simply mean is I am trying to take out the distribution. I'm not putting any distribution to 0.85. If I say it is 0.85, it means it is 0.85, and there is no distribution attached to it, to any values of x, right? In other words, the numbers that you are seeing over there are just simple numbers. They do not come with any distribution. If there is a distribution, there will always be a probability attached to that number. So by doing the conditional expectation, I'm shifting the distribution onto the dependent variable. So I'm saying that given x is 0.85, what is the expected value of y? So y is now the variable which has a distribution. X does not have a distribution, right? So
Okay.
I am not keeping any element of sampling associated with 0.85. So no matter
Okay. So
whatever samples 0.85 comes from, it is always 0.85.
okay. So in other words, we can say that the variables in this linear regression model
Hmm.
uh, should not come with any distribution.
Correct.
Okay. Okay.
Right? Okay. Any other questions up to this point?
Good so far, Tanmay. Thank you.
Okay. Fine. Okay. So the next question that came out over here is, so now from the sample regression function, what I could see is that the observed value is a component, it's sum of two components, the dependent variable, the dependent value yi hat, I mean, the estimated value yi hat plus the ei. And my objective is to minimize the impact of this ei, because lower the impact of ei on my estimators, the more closer will be yi hat to the actual value of yi, right? So how do we do that? So we do that using an algorithm called the ordinary least square algorithm. Now this is another important question which comes in credit risk modeling interviews. They ask you this question, that what exactly is the ordinary least square estimation, right? So this is something that we need to understand, right? Fine. So in today's discussion, we will see how is it that this is, or these ordinary least square estimation is conducted, how is it that these errors are minimized, and so on, right? So this is something that we do in today's session. Fine. So before I start off, just take a minute's time and just go through this entire thing that we have talked about. If you have any question, put it in the chat box, and then I'll take it up from, we can take it up from there. Okay, so let's get started. Fine. Okay, so our objective today is to understand the different ways of minimizing the sum squares of the errors, or minimizing the error component. So what is the error component? In a regression model, the error component is the, so it is that unexplained component in any model, right? And it has a normal distribution with mean 0 and a constant variance. Minimizing the error component. So over here, what we do is, or the way we would look at it is, so the error is nothing but the observed value of yi minus the predicted value of yi. So this is what the difference, so this is what is the error term. So the error component is ei minus this, right? Now, the next question that comes out over here is then that yi minus yi hat this. So now how do we minimize the error component? Now, obviously one of the choices is that you minimize, so your objective function becomes z is equal to minimum or minimize the summation of, right? So basically what happens is, what we have is minimize summation here, right? Now after this, now what is the challenge with this part? Summation, minimizing the summation of ei. Now one thing that you can see is that this error term ei follows a normal distribution with mean 0 and variance sigma square e. Now observe that the mean of this error term is 0 and it's absolutely random. So the implication is that there will be some values which will be positive and there will be some values which is negative. Right, so there will be some values which are positive and there will be some values which are negative, and both of them will cancel out and all of them can cancel out and become 0. So basically your objective function z may be 0, but the actual errors would be very high. Right? So this is one of the biggest challenges of minimizing the summation ei. Because there is a sign right? A positive negative error. Let's say there is an error of -5 and there is a error of +5 and both of them cancel out at 0. But the -5 is an under prediction for 0 and the +5 is an over prediction, right? But the errors actually exist there. But if you do a simple summation, you will see that both of them cancels out at 0, right? So this is something that we would like to reach out. Also, this is something that we need to understand. And that is the reason why, because the plus minus may cancel out to be 0, therefore what we will use is we will use we cannot minimize the summation of ei. So that's the first point. So this moves that. Now if sign is the problem, a easier way to solve this would be to consider it is equal to minimize the modulus of summation. The modulus of summation here. So the question that next comes out over here is that how do we do this? How is it that we can minimize the modulus of summation here, right? So to do this, the next question that comes out to us over here would be, okay, so how do we do this? So let's check that part. Now, what is this? How does this modulus function work? So let's say y is equal to modulus of x or mod of x. Now this is equal to x if so it says that y equals to x if x is greater than equal to 0 equal to minus x if x is less than 0, right? So what it means essentially is that no matter whatever the values are, y will always be positive. So if x is greater than equal to 0, okay, so let's say this is x, so this is x. So over here, let's say y equal to mod x, right? So if x is 1, y will be 1. If x is 2, y will be 2. If x is 3, y will be 3. Similarly, if x is minus 1, y will be 1. If x is minus 2, y will be 2. Something like this. So one thing that you can see is that this is a kinked function. So this is the absolute value function and it has a kink or an edge at x equal to 0. So basically you can see that the function gets only minimized at x equal to 0. So you can minimize the function even only if all the errors are 0. So with positive and negative errors existing out, and if you take out the absolute sign, then you can never reach to a point where this function can be minimized, right? So you can never do that. So it is very difficult optimizing this function. Also, since this function has a kink, the biggest challenge with this function will be that this function is not differentiable. Now, if it is not differentiable, then it is very difficult to identify the or to extract the functional form at where, or the estimator the estimator functions where this function gets minimized, and also will not be in a position to assess, right, that. So basically, because this function is not differentiable, this function will not give you, you will not be able to calculate the functional form of the estimators, which minimizes summation ei, right? Because we require the first order and the second order condition, and we need the function to be smooth differentiable function, right? So that is the reason why this second objective function is also not possible. So the third thing, now the challenge is we need to take care of the signs as well as of the differentiability of the functions. Okay, so now the next question that comes out here is that we need to solve this problem Z with the, so now I need to minimize this, I need to design an objective function which not only takes care of the sign but also of the differentiability of the function. So this is where I get to see this. So in this part, what we do is we minimize not summation ei, not summation mod ei, but summation of ei square, right? Hence, because you are minimizing the summation ei square, this framework is called the least square approach. The least square approach, right? Now, the next question that comes out over here is then how do we go about doing this least square approach, right? So, is it a constraint? So, what type of an optimization problem would this be? So, first, let us try to frame the objective problem, the objective function of the least square approach. Now, before we go into do that, right? So, up to this point, is it clear to us? Any questions up to this? Devoshmita, Deepak, Akhilesh, Vasu, Shashank, you. Okay. So just a quick question, guys. Especially, so this is for those people who had joined in from the other batch. So were these parts discussed in the last in that batch when you were doing scorecards and all? So these aspects of the linear regression model. Okay, so let's move on. Okay, fine, fine. So coming to the next part. So now, what I want to know is that how is it that this model would work now? Okay. So let's start creating the objective function for for the least square optimization. Okay. So now, coming to this concept of summation ei square. Now observe that ei square not only solves the problem with the signs because you are squaring it, and every time you square it, you are solving the problem of its signs, and also because it's a squared function, it is very easily differentiable. So how would your function look like then? So it looks something like this: ei square is yi hat minus yi hat whole square, right? So yi hat is alpha hat minus beta hat xi whole square, right? So now this becomes your objective function, your OLS objective function, right? Now when I have this, so what is the objective next? Now I need to find out that value of alpha hat, or that function of alpha hat and beta hat which minimizes the sum squares of this error, right? So over
So
here,
in this, Dharma,
yeah,
in this function, the sigma ei square gets cancelled out to 0, correct? Based on the values.
which one? I didn't get your
Uh,
point.
so sigma ei square minus sigma yi minus yi at whole square. So
No,
in
this is a
this,
summation. This is a summation,
this is
right?
summation. Okay,
So you are just summing up all the values of ei square. So let's say
okay.
here is 1, 2, 3, 4, 5 records. So for each
Uh-huh.
of them, so this is your actual value, observed value. You'll get a predicted value. For each of them,
Okay.
you'll get an error. You're squaring them up and you're adding up all the square of the errors.
Yeah, correct. Okay.
Right? So now my objective is to understand that what is that alpha hat and beta hat, which would help me minimize the sum squares of the errors, because I have to determine the functional form of the alpha hat and the beta hat respectively, right? So that is what I first need to do. So over here, so my first order conditions, the first order conditions for minimization will be delta summation ei square delta alpha hat is equal to 0, delta summation ei square delta beta hat is equal to 0, and we call these the call these the OLS equations, right? So this is the OLS equation. Now, solving these two equations would first give me, or would give me, the point where the function minimizes, right? And then the second order condition will tell me whether that point where it actually optimizes is a minimum or a maximum or not. So what should be the second order condition? The second order condition should be that alpha summation e square delta alpha second order should be greater than 0. So what should be the second order conditions for minimization over here? The SOCs would be delta beta hat square should be greater than C. Right? So these are the two conditions that you need to ensure. These are two OLS conditions. So if I take these two together, this is called the OLS condition. This is the OLS condition, right? So the entire objective behind this was the OLS. So you have the OLS condition, right? Now the next question that comes out here is the following. That okay, so now what we need to do is we just need to now solve for these equations, the first order, the second order, and we need to check whether the conditions for minimization is satisfied over here or not. So let's take the first OLS equation. I'll not do all, I'll just do the initial bit so that you can get an idea, so that you know the important assumptions that we had held up gets cross-checked. So basically what we'll see is that as so each of these assumptions that we were talking about right at the beginning are not only just assumptions. I mean they are actually the premise of the model. They are actually those necessary conditions which needs to be present there in the model so that the model develops, so that this OLS estimation can actually happen. So let's have a quick look. So the first thing is so delta summation E square delta alpha hat is equal to 0. Right, so basically now if I have to do this, it becomes summation this is the first order derivative, right? Okay, so this is the first OLS equation. Now if you have a look into the calculation very carefully, you will see that what it boils down to is nothing but this. So it clearly says that the summation of EI is equal to 0. So the The first OLS equation tells us that the necessary condition for getting the OLS done is that the summation EI has to be 0. Now, what is the implication of this summation EI? The implication of the summation EI is EI equal to 0 is that E bar will be 0. So, which means that EI will follow the normal distribution with the mean 0. So that 0 comes in from here. Right? So EI square is, so this is the first and the most basic observation that we get to see from the OLS. So this is the fifth assumption that we talk about. The error term is assumed to be white noise, no autocorrelation, and mean is equal to 0. So this is one. So this assumption. So basically, you can do the OLS equation, or I can use the OLS to minimize the sum squares of the errors, if and only if the summation of EI is equal to 0. If that is if, and this is again the reason as to why summation EI cannot be used as an objective function. Right? So is this part clear? Data science interviews, when you go for any data science interviews, that is where they ask you these questions, that why summation EI square, why not summation EI. So understanding these algorithms and how you are getting the algorithms is something which is very important for understanding this, because the approach. So basically the idea over here is that the model development that you will do over here, or linear regression, the area where linear regression will be applied is KD model and LGD model, right? But the question that remains is, why are you applying it over there?
Tanmay,
Yeah, tell me.
how does this equations that you derived, that yi minus alpha cap minus beta cap xi whole square, the second line?
Which one? Which one?
I'm not able to read. What is that? Yeah, this one. What is this?
Yeah, so this is the outcome of derivatives, right? So basically, you have a function over here, summation
Yeah,
yi minus alpha and beta at whole square, right? So,
yeah,
and you have the alpha in there. So basically, when you differentiate this function, what will you get? So if you are differentiating x square, what do you get? You get 2x, right?
right,
Right? So that's where you get 2 into summation y minus alpha hat minus beta hat at xi, right? Now you have that
right,
alpha hat over here. So that alpha hat has also to be
one,
differentiated, right? If you differentiate
right,
alpha hat with respect to alpha hat, you get 1. But alpha hat is
right,
minus 1 into alpha hat, and hence this minus 1 out there. So in the next step, what happens is 2 into minus 2 goes out. Basically, minus 2 is not equal to 0. Now for this derivative to be equal to 0, you must have summation y minus alpha hat minus beta hat xi equal to 0. So this becomes your OLS equation, which implies nothing but summation E is 0.
okay, understood.
Right? Okay. So this is one of the stories. So the first one of the important assumption is that the summation error terms has to be 0, which implies that the mean of the error terms has to be 0, which implies that the error term must be a white noise. Now let's move to the next part. Now error terms being white noise is not only that if the mean is 0, variance is constant, it should also mean that the two error terms are not correlated, right? So the error terms, number one is the error terms are not correlated among themselves, and the second is the independent variables and the error terms are again uncorrelated. Right? So that is another important assumption. So independent term, the independent variable and the error terms are also not correlated. They are separate from each other. Okay, so I will just go back over here. So while I say that independent variables must be non-stochastic in nature, also there should be one more point that they must not be correlated to the error terms as well. To the error terms, right? So they must not be correlated to the error terms. Now the next question that comes out over here is, so let's now look to the second OLS equation. It is delta summation ei square beta hat Okay, so let's have a look into this. So now what I am doing is I am differentiating these values, right? Right. So first what I'll do is I'll differentiate this with respect to, so I'll differentiate this function, so it becomes 2 into summation of this. Now when I differentiate the beta inside, what I get is minus xi is equal to 0. Now when I write this part, the next question that comes out here is that, so what does it transform to finally? It finally transforms to summation EIXI is equal to 0. Right? Now, if you think about this, so this becomes that the covariance between X and E has to be 0. So X and E should not be related to each other. So this becomes another important assumption of the dependent variable, because if X and E are related to each other, then where you will end up with is a problem of autocorrelation. So this assumption, covariance between X and E, would ensure that there is no autocorrelation. Because if X and E are associated, if they are associated with each other, it would mean that there is a systematic behavior between in the model, systematic behavior of the error terms in the model, and hence you will end up with a problem of autocorrelation. To ensure that autocorrelation does not exist, OLS, one of the important necessary conditions for OLS is that covariance between X and E should be 0. So you must not have any association between the independent variable X and the error terms E. Now, the importance of this assumption is that, so if these assumptions or if these characteristics are not present in the model, right, in the data, then the best fit line will not be attained using the OLS estimation procedure. Clear? So each of these two OLS equations would give you two key insights into the model, and both of these two equations will give you an idea about the fact that the model is, or the model can be correctly estimated. Now the question, now another important question is, and the implicit interpretation which lies there is, it also ensures, the OLS equation ensures that so it ensures that your model parameters are also linear, and they are not non-linear. Why so? Let's say instead of alpha hat, right, we had alpha hat squared. Let's say I have in my model alpha hat square instead of alpha hat. So then how would these equations look like? Right? So to get to these OLS equations and to ensure that these, so having these necessary conditions will automatically rule out the fact that the error term is, I mean, these assumptions or these necessary conditions automatically will rule out the fact that the parameters are non-linear. Now, if the parameter is non-linear, then we will see that none of these criteria gets satisfied, right? So now let's first look into the impact that it would have on the OLS equations if the parameters were non-linear, right? Okay, so before I move into this, are these interpretations clear to you guys? If you want me to stop for a minute and you want to go through this, you can do that as well. Yes, so is this part clear to you?
Tanmay, hi. Tanmay,
Hey, hi.
hi. So Tanmay, a quick question. How exactly will these equation of this OLS equation where we are trying to minimize the error component will be interpreted in SAS, right? That's something. So how exactly will put all this into the SAS platform, and
No,
how
you need
exactly?
not put any of these into SAS platform
Right,
because summarizing the entire OLS procedure is
right,
SAS's proc-rec statement. So when you run the
okay,
proc-rec statement, you need to specify the dependent variable and the independent variables
right,
and the
right,
measures that you need, right?
right,
So the algorithm is there inbuilt in SAS, which will generate the
exactly.
report for you,
Right. So we are
right?
discussing the logic behind
So I am discussing the algorithm which is at the back end.
at the back.
Because when someone is appearing for an interview, it's from my experience that
Right.
especially if it's a CCAR profile, CCAR regulatory stress testing profile,
Okay.
linear regression is used intensively there.
Okay.
So interviewers tend to quiz you deep down into linear regression framework. If it's a scorecard profile, they drill you deep into logistic regression,
Okay.
right? So even and most of the framework that and most of the opportunities that you get into risk modeling is around CCAR and scorecards. Now, whatever we have it now, as we the things are there, right?
Right.
Now, I believe coming year forward, and I mean 2020 onwards, the opportunities will start more towards Basel and on the other side of it. Right? Now, because already IFRS 9 models have been built up, so most of the firms are now not really looking forward towards IFRS 9 development profiles. It's more of validation profiles which are coming up around IFRS 9. But CCAR is something which you have to do every year. So linear regression and different variants of linear regression models become very important when you talk about when we talk about that particular profile, because I happen to myself being I myself have been in discussion with two of the banks, one of them being Northern Trust and the other being JPMC, very recently for CCAR profiles, right? Uh, but I could not finally did not reach a point because I'm just completing about 1 year in my present organization. So that's why after the second round, I did not things did not proceed to the HR kind of thing.
Okay.
But in both of these cases, right, both of these are CCAR profiles, and trust me, they had been very stringent on linear regression and time series models. So they just kind of kept on questioning me around those two areas. They did not ask me any questions on how have you. They asked me that okay, you have been into model development profile. what are the models that you have developed, what is the portfolio that you work for, how is it working around, and so on. But after that onwards, we have been talking mostly around, they, like, if it was an hour long interview, they for last 35 minutes they have been grilling me only on linear regression and time series models, right? So understanding this back end algorithm is something which is very important, right? Now obviously, as implementing them in SAS is also important, we'll do it, but having an understanding of the backend algorithm is equally critical, because they come up with questions like these, that can you explain the assumption that a model is must be linear in parameters and non-linear and not necessarily linear in variables. How can you make a variable into a linear variable? What will you look into it? What how do you linearize that? How do you decide the transformation? So these are multiple questions which come out during these interviews, right? So having an understanding of these questions or these areas is absolutely critical for a regulatory model profile modeling profile. Now, especially in a regulatory modeling profile, all you need to it's not only that you need to understand about how the model is going or how the model is working. It is also in terms of how the model is going on and how the model is so it's not about how the model has been built. Also, it involves it requires you to understand whether the appropriate methodology has been used to build the model, right? So whether you are applying the right measures at the right time. So so these are something. And one very important thing that you need to ensure is that before you develop a model, we need to ensure that all the assumptions that the model requires are satisfied. So this is something again which really becomes important, right? So from that perspective, these understanding the back end of these algorithms is important. Otherwise, whatever outputs will come out, that will be generated by SAS itself. We need not bother about
Thanks.
it, right? Okay. And Vasu, I believe you are based out of the US, right? You are based out of the States. So,
No, I'm in India.
oh, you are based out of India. Okay. Okay. So especially people who are working for the American geographies, they have to, because in America the regulatory landscape is totally a different ball game altogether.
Yeah. Thanks, Anand. Thanks for the feedback.
Okay. Fine. Okay, so let's get on. Uh, okay, fine. So up to this point, it's clear for everyone, right? Fine. Okay. So guys, just give me 2 minutes time. We'll come. I'll just come back and we'll get started. Just give me 2 minutes. Okay. Okay, so now our question was that what if the model was nonlinear in parameter? How would or what impact would it have had on the OLS? The OLS equations. Fine. So let's say our equation was something like this. Like this. So over here you see that this alpha hat square is nonlinear, right? Delta summation ei square delta alpha hat. So this implies so this will be yi. So everything else remains unchanged, not much of change happens. Beta hat x. So if you look into the equation, so nothing much changes. It's just that this alpha hat square. So all you get over here is you get 2 into summation error term into -1. But over here you will get an alpha hat because over here you have an alpha hat square, right? So when you differentiate this alpha hat square, you will get a -1 into alpha hat as well. So this 2 is 2 into summation, sorry, 2 into, so this is 4. So what implies is that alpha hat summation ei is equal to 0. So this is the first order condition. So this is what your first order condition would look like if your alpha hat is not linear. If it is non-linear in nature, then your OLS is alpha hat summation EI equal to 0. Now, if this is the case, then you cannot actually ensure that summation EI is always equal to 0, and hence the heteroscedasticity cannot be. The mean zero and the white noise error term cannot be ensured, right? There can be an autocorrelation or an element of heteroscedasticity in the error term. So I cannot clearly distinguish the fact that summation EI is equal to 0, because in this equation what it says is that at least one of the two, alpha hat and summation EI, has to be 0, right? So given that alpha hat is not equal to 0, I know that summation EI is 0. But if alpha hat is 0, then in such a case I cannot ensure that summation EI is absolutely 0 and that the error term is a white noise. Now if that is the case, so then the entire premise of OLS estimation gets flawed, right? So it is these assumptions, the way the assumptions has been created, rules out the fact that the parameter can be a non-linear parameter. So the non-linearity of the parameters have been directly ruled out this uh, of this modeling framework, because if there is a model, a non-linear parameter, and you try to model it with uh, the estimators and the OLS estimation process, then you know that it is hardly possible. It is possible that the measure that you get is not a correct measure. So it may not be the best estimate that you get. The estimate that you get, estimator that you get, may not be a linear estimator as well. So this is something which needs to be taken care of in this particular modeling part, or in this particular portion, right? Right. So is this explanation clear? Wait, I just document this explanation. You may need it for your future references. Okay. The model parameters have to be linear in case there is a nonlinear parameter. In case there is a nonlinear parameter and in case there is a nonlinear parameter and the OLS estimators are used, then cannot always be ensured that errors are white noise. Then it cannot always be ensured that the errors are white noise. Hence, the resulting estimator would also not be. Hence, the resulting estimator will not be unbiased estimate. May not be the best estimate.
Hello.
Hello. Yeah, tell me.
Yeah. Sir, the alpha is like a constant.
Yeah, so the alpha is the intercept term. The beta hat is the slope coefficient.
Yeah. So when will you like if beta is beta square, then you will treat as variable or same parameter, non-linear parameter or non-linear variable.
No. Alpha hat and beta hat are parameters, right? So they are the
Okay.
estimators, right? Now the variable is x, and each of the betas will show the responsiveness of each
Okay.
x's
Okay.
to
Okay.
y.
Okay. Okay. X are like multiple variable that we will feed.
So for each x there will be a given beta.
Okay.
I am just coming to it in the next part. I just finished this. Now
Okay.
we'll talk about the estimators themselves. We'll talk about alpha hat and beta hat,
Okay.
right? Okay, fine. Okay, now let's come. So this is some. So this is all the about the OLS equations that we had talked about, right? Now in the OLS equation, what we are kind of saying is that that there would be summation. So basically, I have the summation. Uh, this is some alpha at summation E equal to 0. So it means that if the parameter estimates are non-linear, then it cannot always be ensured that the summation E is a 0 or not. Similarly, on the other hand, the covariance XE is equal to, now ideally the OLS estimators would, the OLS equation would give us the OLS estimators, right? So we'll start off from each of the estimators one by one. So from the first OLS equation, we got the following. So from the first OLS equation, we had the following expression. Right? So we had this. Now from here, I need to calculate alpha hat. Now first of all, what I'll do is I'll open the bracket and I'll take the summations. So what I'll get is summation yi minus in alpha hat minus is equal to 0. So this means that summation yi in alpha hat. So alpha hat automatically then becomes, so now I'll divide it by n. So my alpha hat becomes summation yi minus beta hat 1 by n y bar minus beta hat. So this is what the OLS estimate of alpha hat is. So I'll say that alpha hat, you write it as OLS is equal to y bar minus beta hat x bar. Now think about this. Think about this equation that we have written over here. Now think about this equation. Now how then, if you look into this equation, how can I interpret alpha hat in a layman's term? Now alpha hat is the intercept term, right? So if I write a equation, straight line equation like y equal to mx plus c, so this is alpha hat, which is that line, right? So now the question that comes out over here is that how do I do it? Yes, so how can we interpret alpha over here? Okay, see, now, now alpha hat. Now let's first look into how an intercept can be interpreted. let's say x, this is y, right? Now this is your alpha hat. So y bar or yi hat is taking the value alpha hat when x is 0, right? So what is alpha hat then? So alpha hat is that component of the average value of y which is not covered by x bar, or which is not covered by the average values of x. So when x is 0, right, which is independent of x. So it says that if the average value of y is y bar, out of that x explains beta hat, then the average value out of that y bar which is explained by x is beta hat x bar. Now the value which is value of that y bar which is not explained by x bar is the intercept. So it is that of the average behavior of y which is not explained by the x's is explained by alpha hat. So this is precisely what it shows. So the intercept explains, so alpha hat is the intercept. And how do you define the intercept? Okay, so the intercept is nothing but it is that part it is that part of the average behavior of the dependent variable which is not explained by the independent variables. Clear? So the way alpha hat, the way the functional form of alpha hat comes in, right? You can see that it explains what intercept is. So intercept is something what when x is 0, what is the value of y? So that is the average value of the dependent variable, which is not explained by the average behavior in the x. So also x bar explains some part of it. Y bar minus beta hat x bar is your alpha hat. Clear? Any questions up to this point? Okay. Okay. Fine. So similarly, we'll have beta hat. Now to derive beta hat stepwise is a bit of a little, it's a little bit of a complicated calculation because both the OLS equations have to be used. So what I'll do is I will not derive beta hat like I derived alpha hat. I'll straight away give you the definition of beta hat. The beta hat OLS is equal to covariance of xy So beta hat OLS is the slope, right? Now let's try to understand what this beta hat OLS expression is. Now I define beta hat OLS as the covariance between xy divided by the variance of x. Now how do I interpret beta then? So let's just draw a straight line first. Let's try to interpret beta. So this is the change in x, change in y due to 1 unit change in x. Due to due to 1 unit change in x, right? So this is something that we have. So change in y due to 1 unit change in x. Now, now the next part that we need to bring in is that how do we relate these two parts? That is, how do I relate the concept of a slope to the formula that I have obtained in beta hat OLS? Now, first of all, it must show me two things. Number one, the change in y with respect to change in x. So let's look into the formulae for covariance. You have covariance xy. So how do you define this covariance xy? So covariance xy is defined as xi minus x bar into yi minus. So now if you have a look into this, so it shows that when xi deviates from x bar by a certain amount. So how do you define deviations here? You define deviations here in terms of its average value. So when a particular reading of xi deviates from its average value, now in response to that, yi deviates from its average value by this amount. So xi minus x bar into yi minus y bar, right? So the numerator at the top gives me the summation of the total change in y with respect to change in x. Now, how do I say that what is this, how much has this total change been, because this is an absolute number. So what I say over here is that with 1 unit change in x, right, due to 1 unit change in x, what is the change in y? So first of all, I must have a measure of variation in x. So how high is the variation in y with respect to a variation in x? So the overall variation in x, right, is given by the variance of x. So variance of x is the average, overall average variation in x. Now, while the variation in x is, or the overall variation in x is Vx, the change in y due to change in x is covariance xy. Now, if the variation in x is unity, the change in x, change in y with respect to x is covariance divided by the variance of x, which is sigma x square. Right? So this is how beta hat measures the sensitivity or the percent or the responsiveness of y with respect to 1 unit change in x. So what does this measure? What does beta hat measure? It measures the variation in y with respect to a variation in x. Right? Up to this point, is it clear? Is the interpretation of alpha hat and beta hat clear? Okay, is this clear up to this point? Great. Okay. So now from here, so over here we get what we get to see over here is that through OLS, you estimate. So through OLS you get the best or you get the you know you get the best fit so you get that alpha hat and beta hat which minimize the sum squares of the errors. So now if you put this back into the estimated regression equation, you will get the best fit regression line. So the objective of doing the OLS equation is to get the best fit regression line. The best fit regression. So yi hat is equals to alpha hat. So in the place of alpha hat, what shall I do? I shall put y bar minus beta hat. So this is beta hat OLS x bar plus beta hat OLS x. So now the next part is so what I'll do is I'll just take this yi hat minus y bar then this beta hat OLS xi minus. So this is the deviation form of the regression line. So your objective is finally is to reach this line finally. Right? So this becomes your best fit regression line. Right? Now the next part over here would be to understand the properties of this best fit regression line. And the next part would be to assess the properties of this best fit regression line and test for the significance of alpha hat, beta hat, and to understand and to assess the properties of the goodness of fit of this model. To understand how to test for the goodness of fit of this regression model, the overall goodness of fit, the individual significance, the issues with this model, and then we extend it to the multiple linear regression model framework, where we talk about not only about so there would be a few more concepts which would be coming in over there, right? Then the next stage would be to extend it to the challenges of this model, where we'll talk about multicollinearity, heteroscedasticity, autocorrelation, and the statistical tests of doing each of these uh, challenge and the ways of testing these statistical issues, right? So that is something that we continue with in our next session. So tomorrow we meet to complete those parts. Tomorrow we'll aim to have a 3-hour session, right? And we'll try to complete the entire testing part and the properties of the best fit regression line, right? So and then we'll see how these results, and when I say we complete this, I also will try to complete it in SAS as well, right? So in tomorrow's discussion, our two objectives would be to complete the best fit properties of the best fit regression line, talk about the best linear unbiased estimator properties of these OLS estimators, and to check and to do the complete the goodness of fit analysis of a regression line, right? So these are the three things that we'll cover in tomorrow's discussion. Right. So thank you guys. Thank you for your time. Let's catch up tomorrow and take the show forward. Thank you. Bye bye. Have a great day.